Welcome back to AI.Code.Cast. You shared this first bad version problem with us, and uh, I gotta say, it sounds like deceptively simple,
Mm,
but I can see how it could get kind of tricky. Ready to dig in?
Absolutely. This is one of those classic problems that really highlights, why picking the right approach for efficiency is so important.
Okay, so let's just start by making sure we're both on the same page here. We've got all these versions of some software, right?
Right.
Each version builds on the last one. And somewhere along the line, boom, bad version.
Yeah.
Now all the versions after it are bad too because they have that same bug.
Perfect summary. You got it.
You got it.
It's like dominoes, right? One bad version and it just topples everything after.
Yeah, like a domino effect.
Yeah.
So our mission, if we choose to accept it, is to find that first bad version, but do it fast, as efficiently as possible.
Right.
I'm already thinking about how I would approach this.
Yeah.
The most straightforward way seems like just checking each version one by one, starting to the beginning until we hit a bad one. Would you call that a brute force approach?
Yeah. You nailed it. Yeah, that's exactly what a brute force approach would be in this case. You'd iterate through the versions using that is bad version function, just testing each one.
Well, speaking of his bad version, I was looking at my notes, and we're assuming we have this, magical function that just tells us if a version is bad or good.
Right.
It's like this black box that simplifies things quite a bit.
Absolutely. It definitely does. And in a real world scenario, this function would represent some kind of automated test or validation process, something that can quickly flag a bad version.
Yep.
But for the sake of this problem, we can just assume it exists and it works perfectly.
Okay, good to know. Back to our brute force approach.
Yeah.
I'm already seeing a potential issue. What if we're talking about a massive software project with, thousands, even millions of versions? Checking them one by one, forget it, that would take forever.
You're absolutely right. That's the big limitation with brute force. The time complexity, we often denote it as ON, means the time it takes grows directly with the number of versions. So if you have a million versions, you're potentially looking at a million checks.
Yeah, not very scalable. There's got to be a smarter way to do this.
There is. And this is where things get really interesting. Instead of just trudging through each version linearly, what if we could strategically eliminate a big chunk of possibilities with each step?
Okay, I like where you're going with this. What if we could somehow, keep having the number of versions we have to check?
Yeah.
It'd be like those guess the number games where you keep having the range until you hit the target.
Exactly. And that's the power of binary search, right? It's about strategic elimination, asking the most informative questions so you can quickly narrow down the possibilities.
Okay, I'm starting to see the light here. So instead of checking version 1, then 2, then 3, and so on, we would start by checking the middle version.
Exactly. Imagine a row of light bulbs. Good versions are off, bad versions are on. You want to find the first one that's lit. So you start by checking the bulb in the middle. If it's on, the first lit bulb has to be to the left of it. If it's off, it's got to be to the right.
That's a great analogy. I can see it now.
Yeah.
So with each check, we eliminate half of the remaining possibilities. That's how we get that logarithmic time complexity, the O log n.
You got it. And to really drive home the point of how much faster this is, think of it this way. If you double the number of versions, a linear scan takes twice as long. But with binary search, you only need one extra step to have that search space again. That's the magic of it.
Well, okay, you convinced me. Binary search is definitely the way to go for efficiency. But I gotta be honest, I'm a little fuzzy on how we'd actually implement this in code. Seems a lot trickier than just looping through versions one by one.
Yeah, it's a bit more involved, you're right, but still manageable. We'd need to keep track of the start and end of our search space, call them left and right. And then each step, we'd calculate the middle index and check if that version is bad, using our handy is bad version function. And based on the result, we update either left or right to narrow down our search.
Okay, starting to get it, yeah.
Yeah.
But before we get into the actual code, any other gotchas we should watch out for? Any tricky edge cases or anything like that?
There's one subtle but important detail we should discuss, something that even experienced coders sometimes trip over, and it has to do with how we calculate that middle index in our binary search.
Oh, tell me more. I'm all ears when it comes to avoiding bugs.
It's about preventing something called integer overflow.
Okay.
Imagine left and right are huge, like the maximum integer value allowed in our programming language. If we just add them together to get the middle index, we could exceed that maximum value, and that would cause an error.
Ah, I see. So it's not just about getting the logic right. It's also about understanding how numbers are represented in a computer.
Exactly. And luckily, there's a clever way to avoid this. Instead of calculating the middle index as left plus right 2, we use left plus right left 2.
Hmm. That seems a bit counterintuitive. Why does that work?
It's all about keeping the number smaller while we're doing the calculation. By subtracting left from right first, it ensures that the sum is always within a safe range, even if left and right are large. Then adding half of that difference to left gives us the correct middle index, but without that risk of overflow.
That's pretty clever. Those are the kind of details that can really make a difference when you're trying to write code that's, robust and reliable.
Exactly.
So we've talked about brute force, the much more efficient binary search. Anything else we should think about before we dig deeper into how to implement all of this?
Well, you mentioned earlier that we're assuming this is a bad version function just exists, right? In reality, how we actually determine if a version is bad could be, totally different depending on the situation. It could involve running tests, checking logs, even getting feedback from users.
That's a great point. It's a good reminder that this first bad version problem is like a simplified model of what you might see in the real world.
Exactly.
The idea of efficiency and picking the right algorithm, that's universal, but how you actually implement it, that depends on the situation.
Exactly. And sometimes there might even be approaches that are even more efficient than binary search, depending on how those versions are structured or how we can get information about them.
Hmm.
But for our deep dive today, binary search is a fantastic starting point.
Yeah, totally agree. Okay, so we've laid the groundwork, we've looked at the high-level approaches. Now I'm really curious to see how we can turn these ideas into actual code, ready to get our hands dirty.
Absolutely. Let's dive into some implementation details. All right, let's get into some of those implementation details. The key with binary search is to really efficiently narrow down that search space. Think of it like, a detective eliminating suspects. With each step, you want to rule out like half of the remaining possibilities.
I like that. I like that analogy.
Yeah.
So how do we actually represent that search space in our code?
We'll use two variables. We can call them left and right to keep track of, the start and end indices of our search space.
Okay.
Initially, left would be 1, representing the first version, and right would be n, which is, the total number of versions.
Okay, that makes sense. We're starting with the whole set of versions as our search space.
Right.
So how do we actually do that halving step you're talking about?
That's where calculating that mid-index comes in.
Okay.
In each iteration, we calculate mid as left plus right left 2.
Right.
Remember that operator, it does integer division, so we make sure we get a whole number for our index.
Yeah, yeah. And we talk about that clever formula to avoid those integer overflow issues, especially when we have a ton of versions. But why are we adding left to right left 2? Why not just right left 2?
Great question. We need to add left to kind of shift our calculation. Right, left. 2 just gives us the middle index within the current search space. Adding left makes sure this mid-index is relative to the very beginning of the entire list of versions.
Got it. Okay, yeah. It's like we're zooming in on a section of a map. The middle of that zoomed in section, we got to adjust it based on where it is on the whole map.
Exactly. Now, once we have our mid-index, we use that as bad version function to check if the version at that index is bad.
Right.
Right.
Okay, so this is where we have to make a decision. What do we do based on whether that mid version is bad or good?
Okay, so if the mid version is bad, we know for sure that the first bad version has got to be somewhere between left and mid, including mid. So we update right to be mid, essentially cutting off that right half of our search space.
Okay, yeah, we're narrowing our focus like to the left half.
Exactly.
What if that mid version is good?
If the mid version is good, we know the first bad one must be somewhere between mid plus 1 and right. So we update left to be mid plus 1, getting rid of that left half of our search space.
Okay, yeah, I see the pattern here. With each step, we're like strategically eliminating half of the remaining versions.
Yeah.
And we just keep doing this over and over
Until left and right meet, they converge to the same value.
Okay.
This means we've zeroed in on the exact spot, the location of that first bad version.
That's really elegant. I love how binary search takes what seems like a pretty complex problem and just breaks it down into these simple, like repetitive steps.
It's a beautiful algorithm, and you know what? It's incredibly versatile.
Yeah.
It's not just for finding bad versions. It can be used to search, like any sorted data set, whether it's numbers, names, timestamps, anything like that.
You said sorted data set.
Yeah,
That's an important point, right? Binary search only works if our data is sorted.
absolutely.
In this case, it works because we know that any version that comes after a bad version, that's got to be bad too.
Absolutely. That sorted property is super important for binary search to work its magic. If it wasn't sorted, we couldn't just rule out half of the search space every time.
Yeah, yeah. So we've talked about using like a loop, that iterative way of
Yep.
implementing binary search.
Right.
I remember from my notes you mentioned another way, using recursion.
Yes.
Could you explain how that works and maybe compare it to the iterative way?
Of course. So the recursive approach, it has the same goal, right? Narrowing down that search space.
Right.
But instead of a loop, it uses a function that actually calls itself.
Okay.
It's like those Russian nesting dolls.
Okay.
Each call contains a smaller version of the problem.
Ah, I like that visual, the nesting doll approach.
Right.
So how does that actually work in code?
So imagine you have this function called findBadVersion. It takes left and right, the indices, as arguments. Just like the iterative approach, it's going to calculate the mid-index and check if that version is bad.
Right.
But here's the key difference.
Okay.
Instead of updating left or right directly in the loop, the recursive approach calls findBadVersion again, but with a new, smaller search space.
Okay.
So if the version at mid is bad, we call findBadVersion left, mid.
Okay.
If it's good, we call findBadVersion mid plus 1, right?
Okay. So each of those calls is like creating a new nesting doll, right? Representing a smaller piece of the problem. And we keep doing this until...
Until we hit what we call our base case. You see, the base case in recursion is like an exit condition. It tells the function, hey, stop calling yourself. In our case, that base case is when left is equal to right, meaning we've narrowed it down to a single version. But at that point, we just return left or right, since they're the same, as our first bad version.
Yeah.
The main idea is that each time we make that recursive call, it's like we're breaking the problem down into smaller pieces that look like the original problem. And we keep doing that until we reach the simplest case, and then we can solve that directly.
That's cool. So we've seen two ways to do this binary search. With a loop, what we called iterative, and then this recursive way. They both have that same O log n efficiency, but they use different mechanisms to get there.
You got it. And which one you choose often comes down to like personal preference or what makes more sense for the specific problem you're working on. Some developers find the recursive way just clicks for them, while others prefer the iterative approach because it gives them more control over what's happening step by step.
Yeah, it's really interesting how the same logic can be expressed in these totally different ways, each with their own kind of pros and cons.
Absolutely. And that's part of what makes designing algorithms so fun.
Yeah.
Often there's no one single best answer.
Yeah.
It's all about understanding those trade-offs and picking the right tool for the job, which is a key skill for any good developer.
Yeah, totally agree. So we've covered, the core concepts of binary search, the two main ways to implement it. Anything else we should explore before we wrap up?
Well, we focused a lot on the algorithm itself, but in a real-world situation, you might run into some variations or have other things to consider, like you might need to find a range of bad versions, not just the first one. Or maybe identifying a bad version is really expensive, so you want to minimize how many times you call is bad version.
Those are great points. It's a good reminder that this first bad version problem, while helpful to understand the basics, is often a simplified version of what you'd actually see in a real project.
Exactly. But the good news is all the principles we've been talking about today, things like efficiency, strategic elimination, picking the right algorithm, those apply all over the place.
Yeah.
Once you get those fundamental ideas, you can adapt them to lots of different problems.
Well said. All right, this has been a really fun deep dive.
Yeah, I've enjoyed it.
We went from understanding the problem to exploring solutions and even comparing how to actually implement them. I feel like my algorithm game just got stronger.
Awesome. And remember, learning algorithms is all about exploring and trying things out. Don't be afraid to play around with different approaches, see what the trade-offs are, and find what works best for you.
That's great advice. Thanks for guiding me through all of this. And to our listeners, keep coding, keep learning, and keep those algorithms sharp. We'll catch you on the next episode. Okay, so we've looked at this first bad version problem from every angle. Brute force, binary search, even how to implement that search with a loop and recursively. My algorithm brain is definitely feeling a workout.
Yeah, it's good to stretch those mental muscles. And remember, practice makes perfect. The more you use these algorithms, the more they'll just become second nature.
True. Speaking of practice, though, I was wondering, are there any other interesting twists on this first bad version thing that we could try out? Something to really test our understanding and make us think outside the box.
That's a good question. And actually, there are quite a few variations out there. One that comes to mind is finding the last good version instead of the first bad one. It sounds kind of backwards, but it uses the same binary search idea, just with a little twist.
Okay, now I'm curious. How would we go about finding the last good version? Isn't that basically the same as finding the first bad one, just like from the other direction?
You're getting it. The trick is the last good version is always right before the first bad one. So if we can find that last good one, we know the very next version has to be the first bad one.
Oh, okay. So it's like we're searching for the dividing line between the good versions and the bad ones, but starting from the good side.
Exactly. And the way we code it up is pretty similar to the binary search we talked about before. We still have our left and right pointers to define the search area, and we calculate the mid-index the same way. The difference is how we decide to move those pointers based on whether the mid version is good or bad.
Okay, so calculating mid stays the same, but the logic for left and right changes. Walk me through that. How's it different?
Sure thing. So let's say our mid version is good. In a regular binary search, we'd get rid of everything to the left of mid because we know the first bad version has to be on the right. But this time, we want to keep searching to the left because the last good version might still be over there.
Makes sense. We don't want to accidentally cut off the last good version too early. So if mid is good, we'd move left to mid plus 1, right? Focusing on the right side now, but including the mid version just in case.
Exactly. We're scooting that left boundary closer and closer to those later good versions. Now, what happens if the mid version is bad?
Well, if mid is bad, we know the last good one must be somewhere before it. So we move right to mid 1, narrowing our search down to the left half, but this time excluding the mid version since it's bad.
You got it. And just like before, we keep doing this whole mid calculation, checking if it's good or bad, and moving left or right until those two pointers meet up.
And when they do, left is pointing right at the last good version, right?
Mm,
So to get the first bad version, we just do left plus 1.
exactly. It's a small change, but it lets us use the same efficient binary search idea in a slightly different way. Pretty cool, huh?
It is. It shows how understanding the problem really well can open up different ways to solve it, even if they use the same basic tools.
It all comes down to thinking creatively and understanding those core principles, which is what makes algorithm design so fascinating. There's always more to learn and new ways to approach things.
Couldn't agree more. This deep dive has been a blast. We went from a real-world coding challenge to all these different solutions and even found some neat variations along the way.
I'm glad you enjoyed it. And to everyone listening, keep practicing, keep those algorithms sharp, and we'll catch you on the next episode of AI Codecast.